the second step after finding the reactions RA and RB, our next step will be drawing the section. See, let's draw a section at a distance x from the free end of the beam. Once we draw a section, we'll get the free body, we'll get a portion of the beam like this. So in this portion, we have the uniformly distributed load, and this uniformly distributed load acts on a span from x is equal to 0 to x is equal to 1.5. So what we are saying, from x going from 0 to 1.5, the beam element will be like this. Now at the point or at the place where we have drawn the section, let's say shear force is V, bending moment is M. Again, write down the equations of equilibrium. We'll write minus V minus 40 into x is equal to 0. Therefore, the value of shear force comes out equal to minus 40 into x. Again, start taking moments about an axis passing through this free end. So you have the bending moment M acting anti-clockwise. This is M. The bending moment because of the shear force V, that will be V into x clockwise, negative. And the moment because of this uniformly distributed load, it will be 40 into x by 2. That will be equal 40 into x by 2. And it is clockwise because it's trying to rotate this element in clockwise direction. So from this equation, we obtained V equal to minus 40x. From this equation, substitute the value of V equal to minus 40x. We get the value of the bending moment in the beam is equal to minus 20x square. Minus 20x square is the value of the bending moment in the beam when the length of the beam varies from 0 to 1.5. Now, we have one more way of obtaining the shear force and bending moment in the beam. What we can do, without writing the equations of equilibrium on any section of the beam, we can simply obtain the value of shear force and the bending moment. The procedure for that is, we'll make use of the equations, we'll make use of these types of equations. We know dV by dx is equal to minus W, that is the gradient of the shear force in a beam, is equal to the negative of the intensity of the load acting on the beam. And we know dm by dx is equal to V. This formula and this formula we have already derived in the previous lectures. Now see, in the span x going from 0 to x going from 1.5, the value of dV by dx has to be equal to minus W, and the intensity of the load acting on the beam is 40 kilonewton per meter. So we'll write dV by dx is equal to minus W is equal to minus 40. Integrating this, so our value of integration goes from x is equal to 0 to x is equal to 1.5. So x is equal to, and the value of the shear force will vary from the free end to its end A. What we do, the point where we have drawn the section, so we will calculate the value of shear force at this very point where we have drawn the section. So we have the limit of integration going from integral dV, where value of shear force will go from 0 to V, because at the free end the shear force is 0, and at the point where we have drawn the section, let the shear force be equal to V. So we have integral 0 to V dV is equal to minus 40 dx, where the value of your x, this variable of integration, varies from x is equal to 0 to x is equal to x. So integrate this, integral dV going from 0 to V is V is equal to minus 40, integral dx is x, so this comes out V is equal to minus 40x, which is same as we had obtained with the help of the equations of equilibrium.